to our free SBI lectures. So this is the part 2 of transducer theory and resolution. If you saw the first part, a lot has been said about transducers. So we're going to look into resolutions today. So we're going to begin with Huygens principle. And that is a principle of wave interference. The Dutchman, Christian Huygens, had postulated that sound waves produced by imaging transducer do not diffract, but they obey the principle of wave interference, otherwise known as Huygens principle. Now, active elements consists of an indefinite number of sound source. Now, each particle on the surface of the crystal can be considered a small individual sound source that produce a little sound wave. So the numerous tiny diffracted wave pattern interferes with each other by creating constructive and destructive interface. And the resulting sound beam shape is the sum total of all individual wavelengths. This image gives you an idea of sound passing through various apertures in multiple checkpoints. So diffraction is the breaking up and spreading of beam from a small aperture. Yeah? So beam profile also depends on diffraction pattern of ultrasound transducers. So when sound waves are produced by a small sound source, approximately the size of the wavelength of the sound, the wave will diverge as it propagates. This divergence or spreading of the sound wave is called diffraction. Pulse produced by imaging transducers do not display diffraction pattern because the crystals act as the sound source is considered. The crystals that is acting is considered larger than the small sound source. Aperture is the width of the sound source. Yeah? Sound from a small aperture will diffract and spread out. This divergence reduces the intensity of the beam. In clinical ultrasound, we want the beam to be very directional. To achieve this, larger apertures are used in which it is significantly greater than the wavelength of the sound beam. This will minimize diffraction and produce a directional and intense main beam. In a single crystal transducer, the aperture is fixed and cannot be changed. It is equal to the diameter of the crystal. In modern array transducers, the aperture can be varied by firing a large or smaller numbers of crystal elements together to form the beam. The variable aperture is just one of the many features of the transducers that have significantly improved the beam profile. As sound propagates into the far field, the beam gradually diverges or spreads out. Now, the greater the distance of the beam, the greater the distance the beam has moved from the transducer, the greater the amount of beam divergence that takes place in the far field. So, small diameter transducers produce more divergent beam in the far field. That's to say, in the far field, small diameter crystals will result in wider beam diameter. As the transducer diameter increases, the beam divergence decreases. As the transducer diameter decreases, the beam divergence in the far field increases. And this sketch shows you the diameter and beam divergence to help you understand. Focusing is the process of reducing beam bandwidth. Yeah? Transducers can be manufactured in such a way as to create a focused ultrasound beam. A transducer with a focused ultrasound beam is one that has its natural beam diameter reduced. Focusing can cause the middle of the sound beam to get narrower, and all modern transducers are focused to produce narrower beam width, and that will mean best image resolution, right? Focusing is mainly effective in the near field and the focal zone. The far zone cannot be focused. Additional benefits will include the increase in spatial intensity and sensitivity. That's to say, the weaker echoes can be detected due to increased intensity. The beam can be said to be focused weakly or strongly, depending on the amount of beam diameter reduction produced. The beam divergence after the beam would diverge after it is focused, which would limit the lateral resolution beyond that point. Now, this limitation of divergence can be overcome by multiple focal zones within the beam. An ultrasound beam can be focused either mechanically or electronically. So, mechanical focusing, let's look at it. Focusing a transducer with an external lens or shaping the crystal is called mechanical focusing. All single crystal transducer were mechanically focused, and mechanical focusing is fixed focus. The position of the focus cannot be changed by the operator. However, many transducers still use a fixed focus to focus slice thickness. So mechanical focus can be subdivided into two categories: the internal focusing and the external focusing. And the internal focusing is done by a curved crystal. The internal focusing was used with large single crystal transducer, and it is not commonly used today, so don't worry about it. External focusing is done using a concave lens or concave mirror. Some transducers today use external focusing with a lens to focus the slice thickness. So, how does electronic focusing occur? This is actually the primary method of focusing multiple crystal array transducer. Now, the main advantage of electronic focusing is that it is variable focusing, unlike the fixed focusing in mechanical. So this one you can actually vary. This means that the operator can change the location of the focal zone as they scan. Electronic focusing has two basic types: the transmit focusing and receive focusing. In transmit focusing, it is applied during transmission of ultrasound pulse. So extremely shortening the timing in nanoseconds are applied to the center of the element in the firing groups. Now this will cause the pulse to focus at a certain depth. Increasing the delay will cause the pulse to be focused at a shallower depth, while decreasing the time delay will focus the pulse at a deeper depth. So transmit focusing allows the sonologist to select the focal length of the transducer. The depth at which this beam is focused is commonly indicated on your scanning machine as caret sign, yeah, or is there's the indicator display by the side of your image. Many ultrasound systems use multiple transmit foci, allowing operator to focus the beam at more than one depth simultaneously. So transmit focusing is the type of focusing that you can control with your focusing current. You are controlling the delay to the center element during the transmission of each pulse. Now, systems using multiple transmit focusing require additional pulse for each focal zone. That's to say, if 5 transmit focal zones are applied to an image, 5 pulses of ultrasound are required to produce each scan line. This means that each scan line and each frame takes 5 times longer to acquire the image. Thus, the scanning frame is reduced by a factor of 5. This makes the multiple transmit focusing a useful feature for abdominal and small part scanning, but it's less useful for cardiac scanning where high frame rates are required. On the side of the receiving focusing, now when an array transducer is receiving echoes, the electronic signals received from each element are summed together to form the echo signal. Now, by varying the time delay during the summing up process, the transducer can optimize the signal received from each depth in the image. However, multiple receive focusing does not degrade frame rate since it is done on reception. Now, the depth of the receive focus may be continually increased as the transmitted pulse travels through the tissue to optimize the reception of all echo. And this ability to decrease it is called dynamic receive focusing, and is applied in the background and does not require any input of the operator. Aperture will refer to the diameter of crystal that is used to generate or receive the sound beam. Now, old single crystal transducer have a fixed aperture that is equal to the crystal diameter. So modern array transducers, which fire small subgroup elements to produce the beam, can use a variable aperture. So higher aperture produce better beam for deeper structures. That's to say, longer near field length, less divergence in the far field. Whereas a small aperture is better for shallower structures. A well-programmed array transducer can vary the aperture on both transmission side and reception side to optimize the beam for each depth, and this is called dynamic aperture. The sound beam is 3-dimensional, having the lateral and the axial limits. The center of the main beam is called the beam axis. So all echoes returning to the transducer from the reflector in any part of the beam cross-section or cross-sectional area at the same depth from the transducer are assumed to have originated from the reflector located on the beam axis. That is the assumption. So when this assumption is broken, artifacts can be seen on the screen. So on our first lecture on SPI, we discussed issues about artifact formation due to the assumptions. So you want to check it out, and you marry the knowledge and it will help you greatly. You know, all ultrasound transducer also generates weaker secondary beams that you call side lobes. Yeah, and side lobes are typically 100th or 1,000th less intense than the main beam. So it means that ultrasound intensity in the side lobe is usually too weak to return echo to the transducer. However, in some situations, these side lobes may be sufficiently intense to cause artifacts to occur in the image, especially when they encounter a curve a specular reflector. Now, let's see image quality, and that's to say resolution. Spatial resolution is the ability of sound beam to distinguish two space adjacent reflector as two different echoes in the image. So as the beam travels through tissue, it encounters many interfaces. The closer the spacing of the interface that can still be distinguished from one another, the better the spatial resolution of the system. And resolution is measured in millimeters. The smaller the number, the better the resolution, the greater the image detail that is displayed. And there are two specific factors or characteristics of pores that determines the ability to produce high resolution or good image quality. And that factors are short pores, shorter pauses, and narrower pauses. And for shorter pauses, you have short SPL, that is spatial pause length, and short pause duration, which is high frequency. Then narrower pauses, you have narrow beam diameter. So let's take a look at the issues within. There are three types of spatial resolution. You have the axial resolution, the lateral resolution, and slice thickness. Now, axial resolution is the ability to distinguish two structures or interface that are close together and lie along the beam long axis, the path of the beam, one in front and the other behind. It is also called longitudinal, it's also called axial, radial, range, or depth resolution. All are one and the same thing. Axial resolution is determined by SPL. So shorter the SPL, the spatial pause length, the better the axial resolution. So SPL is determined by the number of cycles vis-a-vis wavelength. Now, backing materials, if you have a good backing material and a high frequency, it will determine how short the SPL will be. So this also means that the wide bandwidth transducer has good damping. It means that a wide bandwidth transducer has good damping and short pulses. So axial resolution is actually determined by this equation. From the equation, you understand that the smaller the number, the better the resolution and image quality. The numerical value of the axial resolution answers the following questions. How can two structures be, how close can two structures be with one in front of the other and still produce distinct echoes on ultrasound image? So that's to say, as frequency increases, that is shorter wavelength, the numerical value of the axial resolution decreases. This means that higher frequency transducer produces with better axial resolution with higher image quality. So high frequency transducer will produce better axial resolution and good image quality. In addition, transducer pulses are designed with a minimum of 2 to 3 cycles in each pulse. So this also keeps the numerical value of axial resolution low and the image is of exceptional quality. So axial resolution is determined by both the source and the medium. So let's take, for example, we calculate the axial resolution for a 5 megahertz transducer with 4 cycles per pulse in soft tissue. So what do? This is what you do. Find the wavelength by using the wave equation. Find the SPL using the number of cycles, then divide by 2. The axial resolution for 5 megahertz transducer will be 0.6 mm when you do the calculation. Yeah. Now this will mean that the interface that lie at least 0.6 mm apart along the beam axis will be seen as separate echoes. Interface that lie closer than 0.6 mm will not be seen as separate. In fact, they will be seen as single echo. Now, take note, put it in mind that 3.5 megahertz has an axial resolution of 0.6 mm. 5.0 megahertz has an axial resolution of 0.4 mm. 6.5 megahertz has a 0.3 mm spatial resolution accordingly. So the higher the frequency, the better the axial resolution. So axial resolution is the best resolution of all the 3 spatial resolutions. So clinically, the sonologist should try to use axial resolution whenever possible. That's to say, for example, if you want to measure the dimension of a round structure, you place your caliper along the beam axis rather than across it. So because in so doing, you'll be measuring using the axial resolution rather than the lateral resolution. Remember, it's the best, so you want to be more accurate. So let's look at lateral resolution. And this is the ability to separate interfaces that lie across beam axis, that is one beside the other. And it is the minimum distance that 2 side-by-side structures can be separated and still produce distinct echoes. It refers to the resolution that is perpendicular to the axis of the ultrasound beam. The resolution, this is the ultrasound beam, and the resolution across it, perpendicular to it. That's what lateral resolution is. So lateral resolution also can be referred to lateral, angular, transverse resolution, or azimuthal resolution. Lateral resolution is determined by the width of the beam. So lateral resolution is equal to beam diameter. That's to say, if you know the beam diameter, you know the lateral resolution. Lateral resolution in mm is equal to beam diameter in mm. The unit, of course, is millimeter. So since the diameter varies with the depth of the beam due to its hourglass shape, lateral resolution also will vary along the depth of the beam. Remember, sound converge to diverge. So the diameter is not the same across its axis. Yeah. So lateral resolution is best in the narrowest part of the beam, and this is in contrast. It's actually in contrast with the axial resolution, which does not vary along the length of the beam. So lateral resolution is best at the 1 near field length from the transducer, since sound beam is narrowest at that point. So focusing improves the lateral resolution in the focal zone. Good lateral resolution can be accomplished with focusing, either mechanically or electronically. So for example, an unfocused transducer would have the best lateral resolution located at this transition point. And at this point, the beam diameter is always exactly half the diameter of the beam at the transducer. Slice thickness resolution, which is the third resolution in spatial resolution, is the ability to separate interfaces that lie perpendicular to the beam. It is also known as elevation axis resolution or Z-axis resolution. So old single crystal transducers have, they used to have symmetrical beam in which the beam width and slice and the slice thickness were always the same. So the slice thickness usually is ignored. But in all modern array transducers right now, they have asymmetrical beams in which the slice thickness may be different than the beam width. So slice thickness is usually the plane that has the worst resolution among all the planes. So optimally, the slice thickness should be as thin as possible so that the 2D image that is generating and displaying and displayed contains only echoes arising from the target along the central beam axis. But in reality, all sound beams have some degree of slice thickness, which introduce artifacts in the image. So for linear, convex, and phase array, which have rectangular or squared aperture, slice thickness is usually greater than the beam width. That is to say, the lateral resolution is better than elevation resolution. So for these transducers, beam width can be electronically focused and made smaller, whereas slice thickness is usually worse and can only be mechanically focused. So some manufacturers have introduced these multi-dimensional linear array transducers that have 2 or more rows of crystals in the Z-axis that are capable of electronically focusing the slice thickness dimension of the sound beam. So this image will show you the various axes, the axial resolution, the lateral resolution, and the Z-axis resolution. So in summary, all we're saying is that all spatial resolution are dependent upon frequency. In general, the higher the frequency, the better the resolution, be it axial, be it lateral, or slice thickness. A higher frequency will keep pulse short and provide good resolution. A higher frequency will produce a long, narrower beam, longer near zone, or less, and of course, less divergence in the far field. And this will produce good lateral and slice thickness resolution. Now the question is, which is the best among all these spatial resolution? Which is the best, axial, lateral, or slice thickness resolution? Now, axial resolution is the best with a typical value of 0.5 mm. Lateral resolution is next with a typical value of around 1 mm, while slice thickness is worst with a typical value of 1 to 1.5 mm. So this information will help in device production and also to pass your exams, your SPI exam. Play them over and over again and get your notes together. I want you to like, subscribe, and share so that you get the information on notification when we post other SPI free lectures. Also subscribe to our paid classes for general sonography on all specialties. And you can contact me on WhatsApp +234 9019 144175. You can send me an email at sonoeyesdiagnostics@gmail.com. If you have any question, put it on the comment section and we'll do justice to it. Keep learning ultrasound. See you in the next class.